Hi guys, so I wanted to walk you through the remaining notes for section 3.3. So where we left off today is the fundamental theorem of algebra, which basically says that every function defined by a polynomial of degree 1 or more has at least one complex zero. And what that's basically saying is you are going to have some type of zero, whether it's a real number zero or a complex zero that involves an I. You are going to have at least one zero. And then the number of zeros theorem says a function defined by a polynomial of degree n has at most n distinct zeros. So what that's really saying is if you had a cubic function, you would never have more than 3 zeros to a cubic function. 3 would be the most zeros you could have. So that's really what this theorem is talking about. And one word that comes up quite often is multiplicity of the zeros. And that really just means a zero occurs more than once. For example, x minus 2 squared just means you have 2 of the same factor. This would be a multiplicity of 2. X minus 1 cubed, that would be considered a multiplicity of 3. And so sometimes you need to look at the description of a problem and see if you can develop a formula from that. So if you look at this example here, it says find a function f of x defined by a polynomial of degree 3 that satisfies the given conditions. So the first thing it tells us is that it has to have zeros of -3, -2, and 5. So coming over here, I know that my function, one factor must be x plus 3, because that will give me a zero of -3. One factor must be x plus 2 to get that zero, and then one factor must be x minus 5. And so I know I have a basic setup, something like this. Then it also gives me this condition that when x is a -1, the answer or the value of my function should be 6. Well, when I test that in this function, when I plug in -1 for x and set my function value to 6, I don't get the same value. And so this is not my completed function. So what that tells you is there may be a coefficient a that we need to find that will make this function actually have a value of 6 when you plug in -1. And so what I did is I took my basic function and then put a times this, and then I plugged in -1 for x and set my value of my function equal to 6. And then I was actually able to solve for a. And so now what I know is if a is a 1/2, this function, let me scooch that over, this function, -1/2 times x plus 3 times x plus 2 times x minus 5, will give me a value of 6 when I plug in -1. So sometimes when you're given this specific condition, a lot of times you do need to solve for that a value. Now, this work right here is just to let you know, if this was a test question, I would totally accept this answer as correct. My math lab, just so you know, is going to want you to FOIL all of this out and get this in standard form. So that's why I just showed the work here. Let's look at another problem on the next page. So this problem tells us that 4 is a zero of multiplicity 3, and that when x is a 2, the value of my function should be -24. So, because I was given this initial condition, I'm going to set it up as my function is equal to some a value. Because it told me 4 was a 0, but of multiplicity 3, this is my setup. And then I'm going to solve for that a value using this initial condition. When I plug in 2 for x, I should get an answer of -24. And so from there, I'm actually able to solve for the a value that'll make that happen. And so here would be my function. And again, on a test, this would be an acceptable answer, but it does want you to multiply all this out and get it in standard form on my math lab, just to let you know. And so all I did here is I just wrote out x minus 4 times x minus 4 times x minus 4 and FOILed it out. Or if you look back in, I believe it was section R4, there is a pattern that you can use to multiply out cubic terms much faster. But you can also just FOIL it out. Okay, the last thing we're going to look at is what's called the conjugate zero theorem. It says if f of x defines a polynomial function having only real coefficients, and if z is equal to a plus bi, and you know that's a zero of your function, then you also know that a minus bi is also going to be a zero of your function. So sometimes you're going to have complex zeros. So if we look at this problem, it says find a polynomial function of least degree having only real coefficients and zeros of -4 and 3 minus I. Okay, a couple things to notice. You definitely have two zeros, but again, according to this theorem, if 3 minus I is a zero, then 3 plus I will also be a zero. And so it says a polynomial function of least degree. Well, if I have 3 zeros, that means I'm going to have 3 factors, which means my least degree, it's going to have to be a cubic function. Now notice this one did not give us a value of the function. Like it didn't tell us that f of 2 is equal to -24. So in this case, we don't need to solve for a specific a. This is going to be more in general. So here's how I set it up. So if -4 was a zero, one of my factors must be x plus 4. If 3 minus I was a zero, then x minus that zero is a factor. And that also means that 3 plus I is a zero. So x minus 3 plus I must also be a zero. And then what I did on the next step is I just distributed that negative in to get rid of the additional parentheses. And again, now we're going to really have to multiply that out. And so I started with the two more complicated factors, and I used the grid to multiply those out. I just put one on the top, one down the side, and remember, you just fill it in like a Punnett square, and then you can go through and combine like terms. So these two multiplied together got me to this quadratic expression. And then I just took that times the x plus 4 to get my final answer. One last example that I wanted to look at is how you can do synthetic division with complex numbers. So if we look at this example, it says find all the zeros of this function given that you know 2 plus I is a zero. Well, according to the conjugate zeros theorem, that means that we also know that 2 minus I is going to be a zero. That gives you something to start the synthetic division with. So if you come over here, I set up my coefficients. I didn't need any placeholders. And I'm going to divide by the first zero they gave us, which is 2 plus I. And I'm going to walk you through this. I'm also going to show you how you can do this on the graphing calculator. You can also, if you don't have a graphing calculator, you can do this on Symbolab. It'll multiply things out for you as well. So anyways, the process is the same. The only thing I might suggest is that you leave a little bit of extra space between your coefficients because we're going to have to fit some imaginary terms there. So the first term just comes straight down, and then I just multiply the 1 times 2 plus I, which gives me 2 plus I. And then what I do is I just line up the real terms and just add straight down. So -1 plus 2 gives me 1, and then I just bring down the plus I. Now the next step means I'm going to have to do 2 plus I times 1 plus I, which is going to be the FOIL method. But I'm going to have to do this several times, so that takes a while. On the graphing calculator, let's see if I can get this where you can see it. Down here on top of the decimal key, or the decimal point, excuse me, is an I. You can just type these in. So for example, on this step, if I wanted to do 2 plus I times 1 plus I, I'm just going to put parentheses, 2 plus, and just hit second decimal point, and it gives you the I, close parentheses, and then parentheses, 1 plus I. And you can hit enter, and that will do that for you, okay? It'll just save you some time. Like I said, you can also go to Symbolab and do this as well. And so that's where this 1 plus 3i came from. I would line that up. I'd do -17 plus 1, get -16 plus 3i, and then I'd multiply these two together on the calculator the same way. And I would continue until I get to 0. Well, that leaves me with kind of this big giant mess. So don't forget, if I know this is a 0, I also know this is a 0, so I went ahead and I did one more division. Now, this one you could probably do by hand because on the second level, it cleans up pretty nice. So I brought the 1 down, I distributed and lined up my real and imaginary terms. Well, what ends up happening is the imaginary terms cancel, I'm just left with a 3. So then I distribute that to 2 minus I and get 6 minus 3i, add straight down. Again, the imaginary terms cancel, I'm just left with negative 10. And you continue that, and remember this, now that I started with a quartic, this would be cubic, this is now a quadratic. And so then I can just factor what's left. And so my zeros are 2 plus I, 2 minus I, negative 5, and 2. If you have any questions on any of these examples, I believe Miss Ramsey has Liberty Hour on Wednesdays. You are more than welcome to go ask her. You can also check with Mr. Kaiser. He teaches college algebra as well if you have any questions over this.